In the last lecture, we have talked about metals and metallic alloys which are ferrous, having ferrous connections, but now we are going to talk about non-ferrous alloys. This also has very interesting applications. Before starting that, I would like to ask you a question, that what is the material composition of this beverage can? Let us say this is a Coke can. So, what is the beverage composition, the material composition of the can? Okay. So, you can guess it actually, that what are the various materials that is possible. One thing you would notice once you finish up a beverage can is that it becomes quite light when you finish it up. Okay. So, it is metallic A, but it is a very light material, that you may guess. So, that is the clue. So, if you actually really find it out, you will see that that lightness is attributed because of its aluminium base. Most of the beverage cans consists mostly of aluminium, but also it is an alloy. So, this is a non-ferrous alloy. It has 1% of magnesium, 1% of manganese, 0.4% of iron and 0.2% of silicon and a very small percentage of copper. So, that is very interesting, that when we talk about a non-ferrous alloy, this is one of the very interesting example of a non-ferrous alloy. And one of the good thing is that this is made of an aluminium alloy, and this aluminium alloy can be actually mostly derived from a recycled material. So, which means it is actually a very green way of using a material. I have given a site which you can actually visit in order to know more of this type of Coke can, how it is made, etc. So, in today's lecture, we are going to talk about the first of all the various classifications of metallic alloys, and then we are going to specifically focus on aluminium and its alloys, titanium and its alloys, zinc and its alloys, copper and its alloys, nickel and its alloys, cobalt and its alloys, and finally, something which is totally non-crystalline form of metal, that is bulk metallic glass. So, quite a bit of thing we would like to cover in this particular lecture. Now, what are the limitations of ferrous alloys? Ferrous alloys, no doubt they are very extensively used, but particularly for transport applications, for white goods, they are not good. Why? Because they have relatively high density. They are, you can feel that they are very heavy. They have also low electrical conductivity, and also they have an inherent susceptibility to corrosion under certain environments. Let us say under saline water, let us say this Coke can example, for example, its Coke is highly acidic. So, if you put the Coke on a ferrous material, you would see that how it is getting corroded with respect to time. But this particular aluminium alloy composition, it has a very good corrosion resistance. So, the density, the electrical conductivity and the corrosion resistance are some of the important points why one has to go for non-ferrous alloys. Now, the classification of the metallic alloys, if you see, then there is a branch, the ferrous alloys with the base metal as iron, then you have steel, cast irons, etc., and I have covered this in the last lecture. In today's lecture, we are going to talk about non-ferrous alloys, where we are going to talk about various light alloys like from aluminium, zinc, titanium and their alloys, and also heavier alloys, for example, alloys which has copper origin, copper, nickel, cobalt, etc., and their alloys. So, a light group and a heavy group. So, let us first start to talk about the light group, then we will go to the heavy group. So, light non-ferrous alloys, let us talk about it. The first material that we will consider in this is aluminium. Why aluminium? I already told you that aluminium is very abundant in Earth's crust. In fact, it is so abundant that it usually makes no sense that why do not we make each and everything out of aluminium, but we have not made it historically for a very long time, mainly because extracting aluminium from Earth's crust is a very energy intensive procedure. and it was not very well known till about the end part of 19th century that people started to realize, and aluminum at that point of time became a highly fashionable material. In fact, during the Napoleon's regime in France, aluminum is used as ornaments. So, that is how the journey of aluminum started, but people very soon understood the importance of aluminum in terms of transport materials. Okay, so making the sheets, making the radiation fins, making wares, beverage cans, there are many applications. And aluminum has a face centered cubic FCC crystal structure with a melting point about 660 degree. Density is very light, 2700 kg per meter cube. Compare it with steel. Steel is something like 7400 kg per meter cube. So, it is 1/3 the density of steel. Elastic modulus of course is lower, 70 GPa. Steel has much higher elastic modulus. In color it has a silver grey luster and it has high thermal and electrical conductivity. Now, aluminum, one of the very important reasons why it became very popular is that the fuel consumption, the fuel became there was a fuel crisis at one point of time and also a huge pollution. In order to reduce that in Europe, they had to come up with a transport solutions which is based on lighter materials. And there what is found is that if you can replace the car body by aluminum, you can save something like 300 kg weight reduction in a medium size vehicle of about 1400 kg. So, that is very good, because for every 100 kg reduction in the automotive sector there is 20% lower exhaust gas emission. So, and also the proportionally reduced operating cost. So, as you reduce, you are going to gain more and more reduction in terms of exhaust gas and also in terms of fuel economy. That is how aluminum started to be used in many cars. The body is actually substituted from ferrous alloys to aluminum and its alloys. Now, not only in the automobile transportation sector, but today if you look at the aircraft transportation sector, let us say this A340, the wing part of the A340, if you look at it, that is actually made of an aluminum alloy based plate. And here this aluminum alloy based plate, as you can see, this is a wing box here. This is preferred because it has improved toughness, of course lower weight, and it has increased resistance to both fatigue as well as corrosion. So, that is the point why even the aircraft industry has got interest in aluminum based system. Now, there are many alloys. Aluminum is one thing which has been explored with various materials, for example, copper, magnesium, silicon, manganese and zinc. And depending on what kind of alloying is happening, there are different grades of aluminum. For example, the grade 1 is having pure aluminum about 99% pure, and there is this XXX here. The initial XX means actually the percentage of aluminum, and sometimes you will see XX.X series. Okay, when you try to open buy it from the market, it is the digit after decimal is 0 if you see in this X, that means for casting, and if you see 1 here, that means this is ingot. So, that is the kind of way of depicting various grades of aluminum. So, grade 1 is for pure aluminum, as I said. Grade 2 is actually alloyed with copper, that is known as duralium. It is the first material that is used for aircraft applications. Grade 3 is with manganese, grade 4 is with silicon, 5 with magnesium, 6 with magnesium and silicon, 7 with zinc and 8 with other elements such as lithium. And if you get a T, that T means it is also heat treated along with. So, that is how we actually kind of define various types of grades of aluminum. Now, The next thing that became important in terms of transport applications is actually titanium. Its density is actually higher than aluminum, but lower than steel. So, we always say in a density scale, density of aluminum is actually less than the density of titanium, and density of titanium is less than the density of iron based alloys. So, it is about 4500 kg per meter cube. Its melting point is quite high, 1660. Elastic modulus in a pure form is also higher than aluminum, but lower than steel. Tensile strength is about 150 to 500 MPa. It has a silvery grey white metallic luster, and its alloying is having certain typicalities in it. It has basically three kinds of structures. Below 883 degree, it has a alpha structure, which is a hexagonal close packed HCP. Beyond 883, it has a beta structure. Now, you may find out in alloys that it has either an alpha or a beta or near alpha or alpha beta. These two are actually based on the presence of some amount of beta configuration in it. Because of this excellent lightweight, high temperature and good strength, it is having applications in high strength and temperature components, biomedical applications, and also in jewelries, because it has a good luster, as I told you. In fact, there are many aircraft applications where this is used. The alpha phase, there are some of the materials that are generally used for stabilization are aluminum, gallium, and germanium or carbon or nitrogen, even oxygen is used for alpha phase stabilization. Beta phase, there is molybdenum, vanadium, tantalum, niobium, manganese, iron, chromium, cobalt, nickel, copper and silicon. They are used for beta phase stabilization. So, that is the titanium as such. Now, titanium's alloys, let us talk about a little bit of them. Alpha titanium alloy to begin with, that is the low temperature phase. Okay, so, it contains the alpha phase stabilizers, low to medium strength. It has a good notch toughness, reasonably good quality ductility, excellent mechanical property at cryogenic temperature, but it is non-heat treatable, that is the problem with alpha series, and are generally very much weldable. So, example one of them is Ti 8Al and 1 molybdenum, 1 vanadium, weight percent. So, 8% aluminum, 1% molybdenum, 1% vanadium, and rest is titanium, through which you can get a tensile strength of about 950 MPa, and that is used in jet engine components. Because of particularly the cryogenic temperature, it has to undergo very low temperature regions and perform. So, there titanium alloy is very much used. The second group is near alpha titanium, which has not only alpha phase stabilizer, but also some amount of beta phase stabilizer, very low, 1 to 2%. They offer high temperature creep strength and oxidation resistance. One example is that about 6% aluminum, 2% stannum tin, 4% zirconium, 2% molybdenum, you get a much higher tensile strength, 1100 megapascal, and that is used for high temperature jet engine component, and high performance automotive valves, because it gives you a very high temperature kind of performance. Then you have the alpha beta. This one is metastable, that means it is not very much a stable configuration, generally includes some combination of both alpha and beta stabilizers. It is weldable, but if you weld, there is a risk of some amount of loss of ductility. Strength levels are medium to high. Hot forming qualities are good, but cold forming often presents difficulties. Creep strength is not usually as good as in most alpha alloys. One example is titanium with 6% aluminum, 4% vanadium. This is used where low density and good corrosion resistance is necessary, such as in aerospace industry, bioimplants, prosthetic applications. finally, the important one is the beta titanium alloys, okay. And this one is fully heat treatable, generally weldable. It is actually capable of high strength, and also it possesses very good creep resistance, okay, up to quite a high temperature, and cold formability is generally excellent. One of the example is with 10% vanadium, iron 2% and aluminium, you get a tensile strength of 1200 MPa. This is used for many critical aircraft structures such as landing gear applications. As you can see that the landing gear part many a times is made of titanium alloys, which is a beta titanium alloy. So, that is about the titanium alloy. The next is zinc. Now, zinc shares one commonality with titanium is that this is also hexagonally close packed HCP, but its density is very high. See, we are suddenly now jumping from a low density to a reasonably high, very close to iron, 7140. Melting point is also not very high, 420 degrees centigrade. It has a silvery grey lustrous appearance and easy castability. Application of zinc is mostly in terms of corrosion resistance, like galvanic coating, corrosion protection of structures, and also in batteries. And you must be knowing that in our body also we need up to a very small percentage, trace almost, but it is needed so that to prevent to have good immunity, brain growth, to prevent diarrhea, pneumonia and all sorts of such problems. So, that is why zinc to a very small trace amount is generally needed in our body also. So, that is the basic zinc of course. Now, zinc has many alloys which we will talk about, particularly when we will discuss about other heavy non-ferrous alloys. So, when we will talk about non-ferrous alloys, one of the base material is actually copper. Now, copper has a face centered cubic structure FCC, melting point quite high 1085 degrees centigrade, density wise it is heavier than steel 8920. It has a distinctive orange color, as you can see the color, okay. It is used for all the traditional utensils, and it is used because one very important reason that it has a good corrosion resistance. So, it does not get corroded very easily. The other good thing of it is that it is soft, malleable, ductile and very tough. So, that means you can give it various shapes. It has a very good machinability, and it has also one of the reasons why it is used for cooking systems is that it has good electrical and thermal conductivity. In fact, in terms of thermal conductivity, the three materials that are generally used, silver has the highest, next is copper, next is aluminium. And if it is in a very pure form like 99.99%, then it is used for electrical wires, otherwise we use it in terms of alloys. So, it has about 97% conductivity of silver, but the cost of it is 1/8 of silver. So, you may say that this is the poor man's silver. So, that is the good part of actually copper. Now, what are the alloys that copper is generally used to make? The most important one is brass, which contains zinc. Earlier we talked about zinc, and zinc actually goes as a substitutional impurity, which means that copper atom and zinc atom are of considerable size, hence one can be substituted inside the lattice of the other. Also tin, aluminium, silicon, magnesium and nickel and lead are also added. And important thing about zinc addition is that if zinc increases, its strength increases, its hardness increases, ductility also increases, but the conductivity reduces, it comes down. Now, commercially when we get brass, there are two types of brass. One is called alpha brass, which has about 30% of zinc. This has many variations which you know, for example, gunmetal which has 2% zinc used in bearings or bushes, or say gliding metal 5% of zinc used in coins, medals and jewelries, or say Admiralty brass which has about 28% of zinc, 1% of tin, which is used in condensers, evaporators, heat exchangers. Then the cartridge brass which has about 30% zinc, it is also used in ammunition cartridge cases, automotive radiators, lamp fixtures. So, the degree of zinc is much higher there. And if you get even higher percentage, that is alpha plus beta brass, you get things like Mons metal 40% zinc, which is used in architectural works or valve stem, or the naval brass in which you have zinc as well as tin. You get it for marine construction, propeller shafts, so that these things get a very good corrosion resistance. So, that is about the two types of brasses that are used from that are developed from copper. There is of course a very important variation of copper alloy which is bronze. An entire part of the civilization is we categorize it as Bronze Age, right. So, and in it instead of zinc, tin is the main substitutional impurity. Now, this also gives a better mechanical property as well as better corrosion resistance than brass, but it is comparatively hard and it resists the surface wear. For example, if you use the phosphor bronze, about 10% tin and 1% phosphorus, then it is used in music instruments and springs because it has a very good castability. If you go for aluminium bronze, about 11% aluminium and 4% tin, you get a high strength and corrosion resistance and is used in bearings, landing gear components, etc. If you go about 3% of silicon bronze, it is self lubricating, high strength and toughness, and hence it is generally used for bearing cages. Also, copper has two relatively less used, but two important other alloys. Beryllium copper, it has highest resilience, so it is used for spring, screwdrivers, pliers, wrenches, etc. And the German silver, which is about 60% copper, 20% nickel and 20% zinc. This one looks like silver, it has a silvery appearance, but it is not a silver, but not silver. Okay. So, that is because it needs copper, nickel and zinc, and the nickel increases the electrical resistivity, improves strength and corrosion resistance. So, it is not only used for this type of things, but also used for condenser tubes, cutleries, etc. The German silver, which has some amount of considerable amount of copper, some amount of nickel and some amount of zinc in it. So, that is about the copper alloys. Next, we are going to talk about nickel. Now, nickel is also even higher density in comparison to copper, 8900, but it has also a similar FCC structure and the melting point is pretty high, 1455 degrees centigrade. It has also a silvery white lustrous metallic luster. That is why it is used, when it is used with copper, this luster predominates and you get German silver out of it. And application wise, it is used nowadays very much in batteries and also in some alloys with copper, like one is very famous Monel metal, primarily composed of nickel and copper with traces of iron, manganese, silicon and carbon. It has a strong corrosion resistance and it is used in heat exchanger tubes, food processing plant, marine applications, etc. Wherever there is a chance of corrosion, and this is of very good use. Of course, the other use of nickel is in super alloys. Super alloys are something which is used in jet engine blades, and for that you need a high creep and oxidation resistance at a high temperature like 1100 degrees centigrade, and there nickel chromium alloys work in a fantastic manner. So, these are the super alloys where nickel is basically used. Next we are going to talk about cobalt. Okay. So, cobalt already we have seen that it is used with, for example, with steel as an alloy or also with other metals, but on its own cobalt has a hexagonal close packing HCP, density similar to nickel 8900, melting point also is very high, and the luster is silver grey, elastic modulus is about 209 gigapascal, considerable, it is like steel. Main application is for high performance alloys, particularly when, just like nickel and zinc, you need a corrosion and wear resistance, the cobalt comes into picture. Some high speed steels contain cobalt, I already talked about them for heat and wear resistance. Some medical orthopedic implants, cobalt, chromium and molybdenum together, there is a vitalium which is used in medical orthopedic implants, and they are sometimes alloyed with platinum, 95% platinum and 5% cobalt for jewelry applications. Interestingly, it is also having some uses with ceramics glasses to give a distinctive blue tint, cobalt glass, cobalt is also used. So, basically it has a high temperature anti-corrosive applications. Now, finally, so far we have talked about various types of non-ferrous alloys, and but all of them are either having crystal structures like hexagonal close pack structures or FCC structures. Now, can metal not have an amorphous shape, that is, can we not have metals which has no regular crystal structure? Yes, you can, but to do that you have to have a rapid cooling from the liquid state. Now, until recently the cooling rate required is of the order of 10 to the power 5 to 10 to the power 6 Kelvin per second. So fast you are supposed to cool it if you want to really make a metal amorphous. So, naturally, even if you can make it something like a fraction of a millimeter thickness. That means, you can make some ribbons and wires, etc., which you can use for transformer cores or as magnetic sensors. Why should we be going for amorphous shape? It is because with the amorphous shape we are supposed to get more machinability, ductilities, etc., okay, while sacrificing some of the properties, maybe like the thermal resistance or conductivity. Now, the bulk metallic glass is something in which this cooling rate is brought down to something like 1 to 100 Kelvin per second, and that is possible because of some kind of eutectic mixtures that that today we can do for preparing this. For example, you can see that this is a bulk metallic glass structure, and you can see that in the SEM picture that there is no grain, okay, unlike this polycrystalline metal structure where you can see that so many grain boundaries are there. So, as there are grain boundaries, what we are going to get? One is that we are going to get the dislocation resistance, dislocations cannot spread across the boundaries, which means that you are going to get resistance in terms of really forming the system. And on the other hand, in this particular case, you can get a very good formability of the system, but you are going to keep some of the good properties of the metal like good elastic modulus. You are also going to get better properties in terms of some of the things like the resistivity of the systems, etc. So, that is how the bulk metallic glass is coming out to be a very good material which can be used for some of the very specific applications where instead of ceramics, because ceramics are brittle, that brittleness is not there in metals. So, that is where you can actually substitute it. This is one of the example that if you use zirconium, titanium, nickel, copper and beryllium, in terms of a mix, and then if you use this rapid cooling technique, you get a tensile strength of about 2 gigapascal, and a fracture toughness, you get a high fracture toughness 20 megapascal square root meter, and the density is much lower. You see, that is another advantage of an amorphous stage. The density is about 6.1 gram per cm cube, and this alloy exhibits almost no plastic strain at failure, but typically shows up to 2.5% elastic strains. So, that you compare with metals generally, it is something like 0.1%. So, the elastic strain becoming 2.5% is a very high gain. In fact, its first commercial application was in golf club head. So, that is the good part of the bulk metallic glass. So, in this last picture, if you look at it, that in terms of strength, if you can make the glassy alloys, you are going much higher above the steel. That is where is the advantage of the glassy alloys. And if you look at the percentage strain also, you can go much higher above the steel, aluminiums, etc., something like which you can compare only with polymers. So, that is the good thing of it, that you get a much higher level of strain, but high level, very high level of strength. So, that combination makes the glassy alloys like bulk metallic glasses to be a very unique new material. This is where we are going to put an end of our metallic alloys. Okay, so, in the next lecture, we are going to come up with metal strengthening and metal corrosion. Thank you.